Thank you very much, Howard, for the invitation. I have learned a lot of exciting things about differential equations in the past 10 days, and so today I'll actually record lots of things from lots of previous talks. And but let me first start from the main theorem, a little bit of the preparation. So let me just tell a little bit history of special values of L functions, although that today's talk will only care about one L values, but let me just tell some stories along this line. So we start from a fundamental discriminant, and then we consider the associate primitive quadratic character with conductor D. And then, so it goes back to the work of Euler and Dirichlet, that they study the following special value of L function. Let me just, okay, I'll slow down. So let me just give the definition. Primitive quadratic character with conductor D. An example, since Harold asked me to slow down a bit, let me give the example that we're going to use, like chi-3, which is a map from Z mod 3 units to C cross. Here you have map 1 to 1 and the 2 to -1. And that's the one that we're going to use. So, okay, so today we actually don't need L function, but just a special value. So a special value, you can view it as a generalized of zeta values. So this is just a sum from 1 to infinity. We have chi n over n to the k. And let me just say that this is if chi is trivial. So this will give you the Riemann zeta value. We consider k at least 2. So k here is always positive integers. And in other cases, we have k at least 1. So we don't need to worry about any convergence issue here, that this number is always well defined. And then goes back to the work of Euler and Dirichlet. What we know is that this value in the following cases is more or less well understood. So it depends on whether the character is even or odd. Character being even or odd means that if chi -1 is 1, or chi -1, so because chi -1 is order 2 elements, it's either 1 or -1. So in these two cases, then we need to have the corresponding conditions for k. So for even character and the k is even, we know that this number is actually pi to the k times the root of the conductor, and then up to some non-zero rational number. And then in the odd case, we are talking about odd numbers, and we have a similar result. So one way to prove this is using the functional equation of L function and then study the residues at negative integers. Okay, and then the last case coming from k equals to 1. And for simplicity, since we already talked about k equals to 1 for this case, so let me just talk about the even character case. So this is the same as saying, and then also we know about the Riemann zeta value that has a pole here, so D not equals to 1. So in this case, that's the class number formula. If you unwind a little bit of the class number formula, sorry, let me actually finish this part. I'll push the blackboard up. In the class number formula, what does it tell us? It tells us that this L value is actually square root of D times log of some algebraic number which is not 0 or 1. Because this is coming from the regulator in the class number formula. And so this is what we know from Oida and Dirichlet's work about these L values. And as a corollary, so as Wesley said, I'm going to talk about some irrationality results. So let's look at how about these numbers. What can we say about the irrationality or like transcendence of these numbers? So I'll state this as a corollary and put names here. So of course we need these formulas. And we also, let me just use the main theorem due to Lindemann and Wahlstrass. So Lindemann wrote a paper with the correct ideas, and Wahlstrass fills out all the details. So the corollary is like in all above cases, that this L value is transcendence, so it doesn't lie in Q bar. And since Hedwig said we should be like accessible, so let me actually recall what is the theorem of Lindemann and Wahlstrass that we used here. Okay, now write slower. So here's their theorem, and then the special cases will imply all these. So we have distinct algebra numbers, and then we have some non-zero coefficients, which are also algebra numbers. And then, so the linear combination of the exponential of all these algebraic numbers is not 0. So here, distinct just like make sure that you don't have trivial relations among them. Once you don't have any trivial relation among them, then Lindemann-Wahlstrass theorem says that you shouldn't get a 0 number. And then I'll leave it to exercise that you can actually recover that. So here, what we use, so this I'll say imply that pi is transcendence, and also log of algebraic number, so alpha inside Q bar. I actually should use beta, that's how you recover it from the theorem, and not 0 and 1. This one is also transcendence. Okay, so basically it's like, this is what we know from classical theorem, and let's look at a table. So we already know k equals to 1, then move on to k equals 2. For k equals 2, if conductor equals to 1, then we have Riemann zeta value. We know zeta 2 is pi squared over 2, which is also transcendence. Then what's the next one? So the next one, I'll squeeze our theorem here. So the next one is, so we still stick with k equals to 2 cases and look for the next smallest conductor at chi -3. And then we prove this value is actually, unfortunately, we cannot prove its transcendence. We only prove that it's irrational. But we can prove a little bit more. So actually, it's like we prove, so any linear combinations, I said this is pi squared over 6 of 1 zeta 2 and L2 chi are Q linearly independent. So basically, you can also use this. This you can write it as a sum of like 1 over the squares of integers congruent to 1 and the -1 was 3 in this alternating sum. And then you can use pi squared over 6, which is zeta 2 to separate them and get a bunch of other like linear combinations of congruence classes. Okay, so let me just stop for questions. Okay, so yes, okay. Then since Harold mentioned 218 pages, not saying the whole proof is 218 pages, is I'll say if I have time in the end, I'll give another theorem, which is proved exactly using the same method, but a different number to be irrational. I'll save it for later, or you can look at the paper. And then for simplicity, for today, I would like to talk about like the main idea of the proof going to the irrationality of L2 chi, and then so our proof actually has like lots of like each part probably have like alternative ways. So like the 200 pages, like if you really want one proof, you can get a small part from it, and then I'll just explain like some of the ideas. So before that, I want to say a little bit of history before we go into the proof, which also contains lots of histories. Okay, so the remark. Let me just, for simplicity, I'll only remark about zeta k, and you can feel free to think about everything motivically and try to make conjectures about, like, not going into the details. Okay, so this is actually like, I'll say the most important thing before, for our work is April's proof that zeta 3 is irrational. Okay, then I'll talk about the history from there. So today I'm going to give you a very quick sketch of April's proof, and then talk about what the questions raised by people after that, which eventually leads to our proof. And I want to mention like two other work. There's the work of Zuling that he proved that at least one of the 4 zeta values. So one thing is like for all these odd zeta values, you basically expect no algebra relations among them whatsoever from motivic type of conjectures. You can read from Evangel's motive book or other references. And then but you prove that at least one of these is irrational. And along, okay, here is like one number, a couple of numbers, then what we consider infinitely many numbers. That's the work of Revol. Also, there are 2 papers in 2001, and then they prove that infinitely many odd zeta values are irrational. Okay, so let me just write it this way. But what they actually prove is that they prove that the Q linear span of these ones is an infinite dimensional vector space. And then there are later works to improve the dimension bound. And then, so far we haven't explored the potential of our method along these directions. We'll focus on a priori for today. Okay. And then, so before I actually give a priori details of proof, I'll just make another remark is how to prove irrationality okay, so that's the fact which was used in April's work. Is if we have integers, and then so that gives you rational numbers, and then we have a sequence of these rational numbers such that the limit is, this is some number we want to study. Okay, so such sequence is usually called rational approximations to alpha, and if there exists a positive epsilon such that the approximation is very good in the sense the distance between alpha and the rational number is smaller than the 1 over the denominator to the 1 plus epsilon. I'll label this as a star as I'm going to use this later. Then alpha is irrational. This fact is easy to check because it's like if alpha were a rational number, you write it as A over B, and then you can check this will be just O of like 1 over Qn. So that's why if you have a convergence radius, convergence radius will show up later. If you have a convergence speed which is faster than 1 over Qn, then you can conclude that alpha is irrational. So which means that like in April's proof, and let me talk a little bit about history, details to be followed. In April's proof, the hard part for him is to actually find this kind of like rational sequence. Once he had found his sequence actually satisfied its property, then very good, everything is great. And then after April's work, Breaker asked the question about whether you can find like similar rational approximations. And then in Sagi's work, in order to answer Breaker's question, he constructed certain rational approximations, including the one for the L2 chi that we are going to use today. But unfortunately, the sequence doesn't satisfy this condition. So our method is to tell you for still a small number of the sequence in the literature which doesn't satisfy condition but satisfies some other condition that we're going to tell you later, we can still get irrationality. So today's talk, we are not going to give you any new rational approximations as kind of many previous talk hinted on. So today we're going to just use the rational approximations already in literature, but try to weaken this condition. They don't, because if you you don't, for the reason that I asked this to be not equals to 0, and then let me. So if you have like I'll say you start from P over Q and then you multiply it by some integer n, you just make this one stronger. So that's why you don't need them to be co-prime. So if you put them co-prime, this condition is the weakest condition among all these the same rational number. Does that answer your question? All right. Okay, then let me just talk about the outline of April's proof, and also I'm going to talk about some properties of Sagi's rational approximation. So let me actually give some references. So after April's original paper, there's the paper by Van der Putten, where he spelled out details in April's short paper. And then for us, that leads to help us understand like all these rational approximations from a more, I'll say, broader point of view here using modular forms, and that's kind of one way to understand Sagi's construction, so I will recommend Breaker's paper. Okay, so in April's story, what happened is he constructed two power series. With the following properties. I'm going to make a remark about how to understand this property in a minute, but let me just first list the properties. As power series in Rx, so when we view them with real coefficients, we talk about convergence radius with respect to the absolute value on R, then the convergence radii of both A and B is equals to, so this number has an explanation to be explained later. So they have convergence radius to be this number, which is smaller than 1. And then zeta 3 need to show up somewhere. So the convergence radius of zeta 3 times AX minus BX is a number which is greater than 1. Okay. And then the second property is we already know that AN has Z coefficient. So what happens to BN is, so this number is denoted to be the LCM of 1 to n. And then we know that the cube of this number would kill the denominator of Bn. Okay, now I'm going to explain where these two properties coming from. As I think already hinted in Breaker's talk, that what is this two numbers? Is we have x06 plus, so x06 you view it as x1x quotient out by the orthogonal involution, and this one has genus 1, P1, and then it has two cusps, 0, infinity, and with two, this is isomorphic to P1, and with these two to be cusps, and then these two numbers to be elliptic points. Okay, so what is A and B? So A is actually coming from a module form on this module curve. And as Breaker's talk says, that a module form satisfies a differential equation. And then the differential equation, as you would expect, would have singularities as cusps and the elliptic points. So that's why its convergence radius hits the first singular point. And then what's important here is that, so where does B coming from? B coming from the product of A with the rational integral of another module form. And then they have the property that zeta 3, once you kind of like put zeta 3 here, so you can view both as solutions of differential equations, and then it will kill the local monodromy at this cusp. So this cusp, you can see what particular the monodromy type is, and then this linear combination of solution will kill the local monodromy at this cusp, at this like singular point, and hence it's like its convergence radius will extend to the next singular points. Okay, and then what is 3? 3 is the order of the homogeneous differential equation satisfied A. So B actually satisfies, if the same differential operator applied to B, it will give you some like polynomial. So it satisfies an inhomogeneous differential equation of order 3. And then that's the 3 here. Okay, 3 is also like this 3 here. So with all these, now we're going to see what is the, how does it related to the fact here. Okay, so from this fact, since this is a number greater than 1, this will already imply that the limit of Bn over An is actually equals to zeta 3. So we already actually has a rational approximation to zeta 3. We just want to analyze what is the rate of the convergence here compared to the denominator. Okay. So let me just write Pn over Qn equals to Bn over An. And we want Pn, Qn to be integers. So here is like the issue is, although An are integers, Bn's are not. So that's why we need to kill the denominator. Why this property is important? To get P and Q. So for instance, you can take Qn can be defined to be just the LCM 1 to n third power times absolute value of an. One thing is here is, although this condition will force this one to be actually just the positive. Okay, so now let's compute zeta 3 minus Pn over Qn. This is equals to An zeta 3, minus Bn over An. And this is smaller than, so we're going to use this number show up as the coefficient of this one. So convergence radius controls the size. So this is smaller than, so delta is something positive. You could feel free to ignore all the delta that I'm going to write because it's just for preciseness. It doesn't change any of the numerics that we really care about. So this is what's the bound for the top part, and let me just keep the an for the bound of the denominator. And then, so now let's just star, what the star means. So star take log is the same as we want minus log of alpha minus Pn over Qn is greater than 1 plus epsilon times log of Qn. Okay, so this part we already see as like n times log root 2 plus 1, so this convergence radius, and then plus the log of absolute value of an, and we want this one to be greater than 1 plus epsilon. Okay, so Qn, we said that Qn can be taken to be this one. And so by prime number theorem, we know this part actually corresponding to 3n plus little of n. This is from prime number theorem. And then let me just still keep the log an part. Okay, so if you stare at the equation for a minute, so we want some positive epsilon so that this holds. And let's just ignore the part because this is 1 times this one. This is 1 plus epsilon times 1. The key point is like you want this part to be greater than that part. So this is the thing we want to have. So the existence of such epsilon positive for star is the same as saying, in this case, log of this convergence radius is greater than 3. 3 is the power 3 here. Okay, then you can put into your favorite calculator, you see actually this one is true. So this is true. So then, so what actually did is the fact then implies zeta 3 is irrational. Okay, so I want you to forget about all these like simple calculus that I did. This is the only important thing for us here. Now I'm going to spell out for you the property for Zagay's rational approximation and see what's going on here. Yes, yes, yes. Okay. Let me say something that I'm pretty sure about, and I'm going to say I believe it's true. Okay, so the thing that I'm pretty sure about is that yes. I think Vadim already answered questions, and for the sake of time, I'll skip my long answer. And if you are interested, I'll tell you later after the talk. Okay, so now let's move on to Zagay's construction. So, to distinguish from the notation here and also to kind of easily follow the notation in our paper in case someone is looking at it. So let's just say we have two power series. I'm going to recycle, put a prime to indicate it's a different sequence. So we have two power series. Such that let me skip the convergence radii description, but actually talk about everything in terms of differential equations, which I remarked but did not write down. So these two power series, all right? Oh, sorry, thank you. 2x, yes. So these two power series satisfy a linear ODE on P1 with, so these are all regular singularities at 0, 1, 1 over 9, infinity. Okay, now I should tell you what it is. So this is actually Y06. So given that set is like actually, this is constructed using a module form Y06. This is coming from the product of this one with certain actual integral, similar to the Breaker's interpretation of April's proof. And then the second part is this particular linear combination kills the monodromy at the nearest singularity. So this in Rx has convergence radius equals to 1. And then the last property is that the LCM of 1 to n to the power kills the denominator of Bn. Okay, so I think these two are clear. And for this one, it's like, so HA actually satisfies a second order differential equation. And the second order is related to the 2 here. Okay. I did talk about the modular using module forms, how does one get it? But I want to give two, like, I'll put this as a side remark. There's also geometric interpretation, namely that put everything into Gauss-Manning connection. For this case, it was worked out in detail in the work of Verroel, and he actually relates all these things to Verroel's family of elliptic curves. And then in the April case, so in Verroel, so oh, okay. So in his work, so that give you, oh, in her work, sorry, I'm very sorry. In her work, she worked out all the families. Also in Zagay's paper, that there's more than this family of rational approximations. There are a couple of other families, and in Verroel's work, in her work, that she actually worked out how these things related to the Gauss-Manning connection of families of elliptic curves. And then in April's case, that's the work of Breakers and Peters. Okay, so let me go back to this case. I circle out this one here. Now let's just copy it. So I'm going to put the log of the larger convergence radius, so that is 1. And then on the other side, I'll put a 2. And I want this one to be larger than that. This is unfortunately not true. So that's why we cannot, so in other words, star doesn't hold. And what we're going to do is to see what one can do when star doesn't hold. So for that purpose, I would like to actually reformulate this part into something which closely related to Evangeli's work, which was mentioned in both the talk of Van der Put and Bost. Okay. I'll keep this blackboard and call it an easy lemma. We consider a power series and I hope the next condition doesn't look too strange, as Wesley vaguely mentioned in his talk, but I'm going to say a little bit more details. So basically, the idea that you have in mind currently for f, it is a g function. So that's why I hope the next condition is a natural condition for a g function. Okay, so what does it mean? It means that you can find something of the LCM type of format such that it kills the most of the denominator of this g function. So you can think about this as, so this is some g function. And this is at least a property which is conjectured to be true for all g functions. And then you'll see for our application, all these things satisfy this condition. Okay. And then once you have this condition, let me just explain. If b is a rational number here, this, for slightly abuse of notation, this just denotes that you take the LCM up to the integers, the largest integer no greater than bn. Okay. And then for every place v, so v can be p or Archimedean. For every place v, we use RV to denote the radius of convergence of f in the completion with respect to the v-adic norm. And here is like we choose a set of norm which is compatible, so which means the absolute value of p at p is 1 over p. So the condition, actually the general form of this condition and that condition is saying that if the sum of all places that the log of the v-adic convergence radius is greater than b times sigma, then f is a polynomial. Okay, let me make a couple of remarks. First is that for this example and that example, we don't have the m here. It's like we definitely kill all the denominators, which means that they all have this particular form of non-Archimedean like shape that guarantees that, so I'll write this down. In the a priori and the Zaghi examples, we have Rp equals to 1. So that's why it's like in both cases, you only see the log of the Archimedean convergence radius to be greater than something which determines the denominator. The denominator part, which you do not see from radius of convergence. And then to relate it to Boss's talk is that when we talk about like algebraization theorems, oftentimes we are living the world, especially when we deal with p-curvature conjecture type of things, we live in the world that sigma equals to 0. And that's why this is saying that you have some positivity. So one can actually, in work of Boss and Chamalloy, they generalize all these type of things. And then this part can be interpreted as the arithmetic degree of some tangent bundle. And the positivity condition is exactly the positivity condition that Boss discussed in his talk yesterday. Okay. Yes? That's captured in the convergence radius. So if like I have say 1 over p here, and then when you look at the periodic convergence radius, you see like how large that power is. Yes. And I think if you read either the Andre's book or the work, the DGS, the work Savinan, and sorry, so the famous DGS book on arithmetic of differential. Yes, thank you. The work Giotto and Savinan. So in their paper, it's like you see it's like for G functions, there's two things. One is called sigma, the other is called rho. And the rho is capitalized the convergence radius. And the sigma is the sum of the convergence, the sum of inverse of the convergence radius with this B sigma part. Yeah, so these are all like, I'll say classical invariants in G functions. Now, yes. Yes. I'll finish this one, and then we'll take a break. Yes. Okay. So the proof of the lemma is I'll just say definition, Cauchy's formula for convergence radius, product formula, and a prime number theorem. So I'm not going to give the proof, but I'm actually going to talk about what does the ESI lemma has anything to do with on the top of the blackboard and the classical thing. So ESI lemma to, let me just say zeta 3 irrational. In this case, the proof goes this way, which we are going to also mimic it, is that assume for contradiction, zeta 3 is rational, then we can take fx to be zeta 3 ax times bx. Then it's like we have R infinity equals to this number. As I already remarked, Rp equals to 1. And you see it's like B equals to 1, sigma equals to 3. So it means that we have actually sum of log Rv is greater than B sigma. This is checked. The ESI lemma implies that f is a polynomial. And this gives you the contradiction because from the construction that you see is like f is not a polynomial. Because, okay, there are multiple ways to see it because these have like meanings as modular forms that you see this is definitely not a polynomial. And then another way to formulate it is like they satisfy a differential equation, and then you can look for the local monodromy of fx around this point, and then you see it doesn't have trivial local monodromy, hence it doesn't extend over, it is not a polynomial. So that's the contradiction. Okay, so let me just say what's going to happen after the break is like we see this is the condition that we have for the classical method, and then our method is to make this part larger and that part smaller so that it will be hold for more general cases, yeah, including the gauge situation. Okay, then let me just continue with that. We want to get this part larger and that part smaller. I'll start from this part larger because we can actually make this part much larger than the convergence radii. And that I would like to refer to Boss's talk. It's actually like when we consider the sigma equals to 0 case, namely it's like we, in the end of the day, restrict ourselves to, say, the P curvature conjecture to the algebra functions settings. There has been a lot of work on this direction. I'm just going to mention some names and then focus on Evangeli's work. Okay, so some history, sigma equals to 0 case. It goes back to the work of Barreau, which later generalized by the work to a like periodic case to actually prove rationality of zeta functions. And then there's the work of Podia, mentioned in Wessing's talk yesterday, and there's also the like eidetic version due to Bertrandis. And in all these work, they give you like generalizations of like what type of radius that you could consider. And then there's also Evangeli's work, which based on the work of Chernovsky's. And there's also the work of Boss, where he put everything into a more geometric setting in terms of like formal schemes in quasi-projective schemes, instead of just here we talk about like power series, like convergence radius. So okay, so I'll focus on Evangeli's work because for his particular generality is the one that we need to carry out our work. And that's exactly the same work of Evangeli mentioned in Van der Put's talk. So hopefully, like after this part, I'll give you a sketch of proof why like being an exact differential form is a local to global condition. Okay, so for this part, let me just spell out the setting. So instead of consider convergence radius, you have seen this in some format in Wessing's talk yesterday, but let me just spell out all the details here. So this is a book and this is a paper, and each contain different level of different details. So I'll still do the sigma equal to 0 case first, but you'll see how it's generalized. So we consider now a power series with only finitely many primes in denominator. And then for each prime, we pick a phi v, which is from the, this is the open unit disk. I welcome you to think about everything in the Berker setting, like as Pradita talked about in his talk. That's a like convenient setting to think about all these things. And so you can view this as a change of coordinate in the following sense, is that we pick this one such that when you change coordinate, let me write this with coordinate zv. When you change coordinate, this is a v-adic meromorphic function on the open unit disk. Okay, so why is this one related to the above case? It's like if I just do the simplest like change of coordinate, namely change x by like c times x, just looking for disks and centered at 0, and you are looking for the largest disks such that it's a meromorphic function on the disk, that's definitely something larger than the convergence radius. Okay, so when I say this, you'll see as the radius is now captured as the derivative of this function at 0 is the perfect replacement of radius above. Because the scalar, when you do the scaling mapping, the derivative at 0 is exactly how do you kind of make a unit disk into a disk of like convergence. Okay, so that is the replacement for the convergence radius, and then we just do the same thing for all places. If this one is greater than 0, I see something familiar from, yes, thank you so much. Yes, and then F is algebraic. So here algebraic means algebraic over QX. And this is exactly what showed up in boss talk yesterday. Yes. I'm going to say more remarks. So the way to relate it to boss talk yesterday is that you can view F, you can look at the graph of F inside A2. You can put A2 inside P1 times P1 or P2, whichever you prefer. And then you can run his argument yesterday. So this is centered at 0. 0 is the like OK point, like in his talk yesterday. And then you are asked whether this one is algebraic or not, namely whether it is a germ of an algebraic scheme or not. And then these ones in both work with Shambhala, they actually interpret this, as I said, like related to the positivity of the arithmetic degree. Yes. Let me do an example. Yeah. It's like if we know that F is convergent on, say, a disk centered at 0 and with RV. Okay, and then we're going to take our phi V to be the map, which I will say is D01 to the isomorphism scaling map. And then in this case, we'll have the derivative of RV at 0. The V-adic norm is exactly equals to RV. Yes, and the interesting case, I'm going to give you an example to solving this problem. Yes. Okay, so, but before I do the example, let me just upgrade it. As I said, it's like, this is the sigma equals to 0 case. And then you suddenly feel there's something not quite right. Let me put this as a homework problem. Wesley already talked about it in his talk yesterday, but I'll let you see the link by yourself since Harold asked for an example. So the example is like, we're going to take F to be log 1 minus x. And if I want to take phi p equals to identity and the phi infinity to be the Riemann map, such that this is isomorphic to this is the big C minus, so 0 maps to 0. 0 maps to 0, sorry, that is important. 0 maps to 0, and then this is 1 infinity. We remove the slit, and then you write out the Riemann map, and this Riemann map has the derivative at 0 of value equals to 4. And that was actually in Vadim's work that Vaseline cited yesterday. As an obvious thing, if you want to make the left-hand side larger, the first step you would do is to kind of look for some simply connected domain instead of just a disk. And Vadim did some work and have some applications to irrationality measures. No, welcome you. Yes, exactly. Okay. And then I said something goes wrong not very wrong, is that if you're only going to copy this sentence, you just feel it's like, that's definitely not going to prove that the log is an algebraic function. That's definitely totally wrong. Yeah. And then that's why we first need to modify this one. But before I modify this one, I do want to relate it to Vanderpool's talk. Is like when he mentioned that Andre's work, what happens in the application to the p-curvature situation is, as Boss actually hinted yesterday, is like you have the sum of the non-Archimedean part to be convergent, and the Archimedean part, once you have like 9 bundles, or when your differential Galois group is commutative, you can reduce everything to like a commutative group scheme. Andre has a high-dimensional version of it, and hence it's like you take its like the exponential map, the Lie algebra to the commutative group scheme, and that side you see that the Lie algebra is C to the n, so it has like infinite convergence radius. That's why you are in this situation that you have something infinite plus something convergent for the non-Archimedean place. Hence you have positive, and then you get algebraicity results. That's the Grothendieck-Katz conjecture proof. And the Boss' work is to generalize these two foliations that using his geometric interpretation. Okay, so this is the algebraic story, but I put this as a homework, so we're going to see, as Javier hinted, we're going to see the like positive sigma situation, which actually, push this up. I want to put it on the same blackboard because it is interesting that someone already worked out the more general case in his early work and decided to skip that part in his later paper. So actually, in Andre's book, he already talked about the general case, and then let me just state it in the way that is closely related to our work. We consider a couple of finite many power series. Let me just introduce some notation that I'll use later. And we kill the denominator. And we have this like convergent property. But one thing I should have said, this is the Fi composed with 5e. One thing I should have said is like for technical reason, we assume 5e to be equals to identity for almost all v, but that is like not necessary. So this is meromorphic on the open unit disk. So the version is like if we have sum of this replacement of radius greater than, okay, so I said these are the improvement of the left-hand side, so I still copy the same right-hand side. If this is true, then we have the conclusions m is smaller than some explicit bound in terms of all these 5e's. Okay, so what's the difference between this one and that one? Is that if we start from one function, and in the sigma equals to 0 case, then you can see it's like powers of f definitely share the same convergent property. And that's why you see that it's kind of like smaller than a finite number. So that's why f is algebraic. But once we put into the denominator property, you can no longer take power because it's like for log. In the log case, I can take b equals to 1, sigma equals to 1. But if I take log square, there's no way that I can take b equals to 1 and sigma equals to 1. And that's why you wouldn't be able to conclude that it is algebraic. Instead, what's going on here, related to why we call this arithmetic homonomicity bound, is I'll put this as a corollary. If we start from an f, we can consider its arbitrary power of derivatives multiply by the suitable power of x, so that like you don't mix the denominators too much. And then so these ones will all like satisfy the same convergent and the denominator properties. So this form a finite dimensional vector space over Qx. Sorry. So these are linearly independent over Qx. Thank you. M is the number of functions. Yes. So this thing which just said is if you start one f, how do you construct more f's? You just take its derivatives. And then they satisfy the same denominator and the convergent property. And then Andrews' theorem tells you that they form a finite dimensional vector space, so i.e. f is polynomial. That is definitely not a contradiction. Log satisfy a finite order differential equation. Yes. Yes. I also want, so what I actually want to do, let me put it this way, what I actually want to do is I want to apply delta equals to x ddx. Okay. Yes, so that's the correct version. But you can multiply by x to them as their like linear span is the same. Yes, 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 exactly. Okay, so, and that's what we are going to use. Let me put it this way. I'm going to tell you what is the phi that we're going to use for the Zaghi situation. And then as you see here, is like we will construct a bunch of functions, and then they satisfy differential equation, and then you look at the, like, actually as Javier suggests, you look at the D module generated by them, and then we have, goes back to Andre's work. He gave you an explicit upper bound in terms of like all these auxiliary choices that you make. And the hope is like, then there's some contradiction to be drawn. Related to here is like, so here you can view as your upper bound is dimension is 1, because it's like, it is a polynomial. Polynomial the same as saying it's a Qx vector space of dimension 1. And then here, instead of having a polynomial, we have a finite dimension, and we hope to draw some contradictions from there. And okay, then why didn't Ivan J prove that one? Because the bound that he has is not yet good enough. And I want to make a remark which I'm going to spell more details later. So this is the remark. Go back to our work on unbounded denominator. We try to improve the bound. And what's very important for us is the work of Boss and Shaw that Vasily mentioned yesterday, that this is very essential to inspire us for the like optimal bound that we want to have, and then we improve the bound further for our application. So this is just, they all give you sharper bound on n. And that's crucial for our application, which I'm going to explain why. Before I move on, questions. So the next two things I'm going to do, one, tell you what are the phi we choose, and second, how do we actually finish the proof? What do I mean we want a good bound? Okay. So back to Zaghi's construction. Okay, so the first thing is like, there's something that we really don't have choice, is the work of F phrase that I interpreted over there suggests that we're going to say assume for contradiction this L value is rational, then we would have a function H is given by HB minus this one times HA. So this will be a Q coefficient power series. And from this one, it suggests that we're going to take B equals to 1 and sigma equals to 2 in that setting. Okay, and since we so far don't have much knowledge about what's going on at the Archimedean places, so I'll just take phi p equals to the identity. This is okay because you can check that the periodic convergence radius are all at least 1. Okay, so like what is phi infinity? Let me start from a map that we already seen multiple times, is the lambda map, the Q expansion of the lambda map. The formula doesn't matter for us at all. What is important for us is that there's a 16 here, and the lambda has the property that it is a universal covering away from 0 to 0, and we know that 0 maps to 0, and the preimage of 0 is just 0. Okay, then what does this property say? It says it's like if F is a formal power series satisfy a linear differential equation with singularities. Yes, I'll slow down after I give you the statement. With singularities in 0, 1, infinity, I'll state this as a fact. Once I state the fact, I'll pause, let you think. Then, F composed with lambda is actually convergent on the open unit disk. Okay, so F is a power series, and with singularity 0, 1, infinity, which means if I look at F at a x0, not 0, 1, infinity, at a good point, then it's, as a linear ODE by Cauchy's theorem, it's convergence on its universal covering. But then we already know that it is a regular function at the singularity 0. So we can add the 0 back, and then we can add the 0 back in this way. So once you only have 1 0 in your preimage, there's no monodromy around there that you need to worry about. So that's why F pullback by lambda is convergent. Yes? Yes. It's just this is, I'll say this contains Y2. Yes, thank you. Okay, so now it's like, what are we going to do? We're going to compare this one to that one. That one is like, we have one more singularity, 1/9. So unfortunately, we're doing this kind of like, not very smart thing, but it does give you a large derivative. It's like, so we just say it's like, this picture is not too far away from the picture for Y06. Is now we can take, so if omega contains D as a domain such that the preimage of 1/9 is just 1 point, just 1 point, and it equals to the preimage of 1/9 closest to 0, then we take our phi infinity to be, so from D to omega simply connected. So this is the Riemann map, and still 0 maps to 0. And here we do the lambda map to C minus 1. By the same kind of topology argument, it's like one preimage of 1/9 is okay because we have this over-convergent property, and because there's no more further kind of preimage, so there's no other monodromy to worry about. So what we have is that phi H composed with this one is convergent on D. Yes, yes. For this application, we don't. Yeah. Yeah. Okay, and then we'll say it's like although because we choose a D so that the radius shrink, it's no longer 16, but I'll state this as a fact. You're welcome to look at our paper for pictures, is that we can find a large enough omega such that the derivative at 0 of phi infinity is greater, if we take log, is greater than 2. Because it's like the 1/9 pre-images, like our control, you know where they are, you can kind of chop them out, and it doesn't chop out too much of the space, and then you still have this condition to hold. Okay, so what do we have? It's like we have a bound, and now I'm going to explain how are we going to use the bound. So what do we have now? On one hand, it's like we have an upper bound. So we have an upper bound on the QX dimension of all such functions. By all such functions, I mean that with the convergence property with respect to these phi and with the control of the denominator. On the other hand, what are the functions? So the actual functions. So we have constant function 1, which is very nice. And then we also have log 1 minus x. The denominator you can check directly. And for the convergence property, we just use the fact it satisfies differential equation with singularity 1 and infinity. So the same argument holds, that it's convergent after you pull back by phi infinity. The functions which satisfy the condition Cn equals to z, f such that phi infinity composed with f is convergent on the disk. Yes. Now we also have the Li2, which is xn over n squared. I need to look at my cheating sheet. And then we also have this function, the first log function, take the square. This is also okay. And then there's the fifth function, which Wesson gives in the integral form. And then I'm just going to give it using our best friend hypergeometric equation. So it's this one. Okay, so we have 4 functions, which probably you've noticed it after I raised this question to you. And there's a 5th function, which actually it honestly, so you can think about y as coordinate of x0, 2. So on x0, 2, there's a such function. Of course, you can pull back to x2. And then we also have our h. And then we also have the derivative of h because it satisfies a second-order differential equation. And then one more thing is we observe is like things doesn't get too small if I also put an extra condition that phi 1 over negative 1 over 8 is 1 point, and which is the closest to 0 pre-image. Because I want to use this, like we want to actually use this symmetry. So the symmetry will give you 2 more functions. Okay, so on one hand, we have 9 functions. On the other hand, you ask, what is our upper bound? Unfortunately, our upper bound is smaller than 9 functions. If we ask you this particular question, that's sad. But we can actually finish the proof by the following, is we finish the proof. Let me use that part of the blackboard. We finished proof by looking at, we push everything to x2, which you can do like by, taking symmetric like arrangement of these functions, then you can push forward everything to x2. You don't gain or lose anything. It's just that your denominator type gets changed to this one. The derivative also kind of like squared, so it doesn't get things worse. And then we put an extra n here. So putting an extra n allows you to just take certain integrals. And once you take, so this is take integral once. And when you allow this one, it's like we actually have 14 functions here. On the other hand, our upper bound, I think, okay, probably the best one we wrote in the paper is smaller than 13.6. Then this gives you the contradiction. Okay, let me explain this one more time. Is we have these honest 5 functions which exist no matter what. And then we assume for contradiction that this one is rational. Then we have 4 more functions. And then once we take the integral of all these, we get 5 more functions. And then we apply our bound. And our bound is something like smaller than 14 functions. So that gives you the contradiction, which says that these functions which are supposed to not exist should not exist. 0.6. Yeah. Just want to give you a feeling on what type of bound we get. Less than 14 is the key point. Yeah, I agree. But actually, the integral idea came before we found that function. So it's kind of like desperate whatsoever. So, and then that gives us the contradiction. And let me just summarize what's going on. In the sense, it's like we use the classical rational approximations, and then now we weaken the condition to this one. One thing I lied a little bit is this is the denominator without putting the little n. You don't want to just add a half for that one n. That will definitely kill the problem. You want to do some sophisticated changes, which I do not have time to explain. So I'll just say there's something one does there. So you first have a larger radius and some small adjustments for the denominator for this condition to hold. So that's step number 1. And then in classical situation, once you have star condition hold, you're done. We're not done. It's like now is we end up in the situation, it's like you have a finite dimensional vector space, and we know some candidate, and we have an upper bound. We want our upper bound to smaller than like the candidates that we can write down based on the irrationality assumption. Based on the assume for contradiction assumption. And then we're lucky in this situation. And in our paper, you can find another example, which is product of certain log values, which we are also lucky in the setting that we can finish the proof there. So let me finish my talk here. Thank you so much.